SwayamPrabha. Digital India. Educated India.
In today's lecture, we start a new topic, namely dimensional synthesis of linkages. By dimensional synthesis of linkages, we mean how to determine the kinematic dimensions of a linkage so as to satisfy some prescribed motion characteristics. Now, we have chosen already the type of linkage. We have to only determine the kinematic dimensions such that this particular linkage will be able to satisfy some prescribed motion characteristics. Now, the prescribed motion characteristics can be done in various different ways, and accordingly we classify these problems of dimensional synthesis of linkages. For example, the first class of problems can be called motion generation. By motion generation, which we may also call a guidance problem, what we mean that we have to design the linkage such that a rigid body, for example, that rigid body may be the coupler of a 4R linkage, which is a floating link, which can be guided in a prescribed manner. That means we want the coupler to go through various prescribed configurations, that is guiding the coupler in a specified manner. Now, this guidance of the coupler may or may not be coordinated with the input movement. That is, the requirement may be such that I do not mind what is the input movement so long as the coupler is guided along in a prescribed manner. In another type of problem, we may need that as the coupler goes from one configuration to another in this specified manner, the input link must move by a definite amount, by a prescribed amount. In that case, we say that this is a guidance problem or a motion generation problem coordinated with the input movement. Let me now clarify this particular type of problem with the help of some models. As an example, let us look at the model of this 4-bar linkage. Here, this is one of the link which is connected to the fixed hinge. This is another link which is connected to the fixed hinge, and this is the coupler. Our objective is to use this coupler as the desk of a writing position. Right now, the desk is folded such that the student can sit here, and there is enough space between his leg and the next row of desk. Now, this coupler can be moved such that it comes to the writing position, and now the student can use this coupler as his writing desk. As we see, here is a stopper such that the coupler cannot move anymore. And when the job is done, he can fold this writing desk and take it away while leaving his seat. So, this is a motion guidance problem that I want the coupler of this 4-bar linkage to move from this configuration to this configuration in a prescribed manner. There is no need to coordinate this movement because our objective is to have it locked at the writing position, and we can take it away to the folded position. So, this is the example of a guidance problem or a motion generation problem without any coordination with the input movement. Next, we see the model of another 4-bar linkage which is used as a tipper dumper. Let us now look at the model of this tipper dumper. Here, the dumping bin is the coupler of a 4-R linkage consisting of this yellow link and this green link. This yellow link is connected to the fixed hinge mounted on the body of the truck. Similarly, this green link is connected to the fixed hinge which is mounted on the body of the truck. So, of this 4R linkage, this dumping bin becomes the coupler. Our objective is to make this dumping bin move in a prescribed manner from this transport configuration to this dumping configuration. This 4R linkage is driven by a hydraulic actuator such that link 4 is used as the input link and it is moved by this hydraulic actuator to move the dumping bin. This is again a guidance problem that I want to guide this particular coupler from this transport configuration to say this, then this, then this, and finally to the dumping configuration. So this is again a motion generation problem without any coordination with the input movement. We then will see another model of a little more involved linkage with the guidance problem. That will be the model of a rail-less garage door. Let us now look at the model of this 6-link mechanism. Here we have the fixed link 1, then 2, 3, 4, 5, 6. So this is a 6-link mechanism, and this mechanism is mounted on the sidewalls of the garage. The car is inside the garage. This is the roof of the garage, and this link represents the door board. So while the garage is open, that is the car can go out, the door board is parallel to the roof. Now to close the garage, the door board is moved such that the garage gets closed. So this is again a guidance problem. I want this particular rigid body, that is link number 6, to move from this closed position to the open position in a prescribed manner so that it does not hit the body of the car. These mechanisms are mounted on the sidewalls, so there is no obstruction with this with the car. It is only the door board which moves inside the garage and closes the garage or opens it. The thing to note that there is no prismatic pair. The entire mechanism consists of only revolute pairs. So this is the open position of the garage when the car can move out, and the door board is parallel to the roof of the garage, and in the closed position it becomes vertical. So this movement from the vertical to horizontal position must take place in a prescribed manner. This rigid body must be moving in a prescribed manner as it goes from between these two extreme positions. So this is another example of a guidance problem. So we have seen 3 models to explain what do we understand by a guidance problem. That is a rigid body, which was the coupler in case of 2 4R linkages, which has to be guided in a prescribed manner. The next class of problem we call a path generation problem. In this type of problem, a point on the floating link, that is the coupler of a 4R linkage, is to be guided along a prescribed path, and this guidance of that prescribed along that prescribed path may or may not be again coordinated with the input movement, just like the guidance problem. Whether we are only interested in going along a prescribed path by a particular point of the floating link like the coupler, or the movement along that path also has to be coordinated with the amount of input movement. Again, we will see some examples of this path generation problem through a number of models. As an example of a path generation problem, let us look at the model of this 6-link mechanism, which can be used as a dual mechanism. In this mechanism, we have a 4R linkage consisting of link number 2, link number 3 and link number 4, where 1 is the fixed link. So this is a 4R crank rocker linkage. The 2 revolves as a crank, The thing to note that this particular coupler point, we want to generate this particular prescribed path. This path consists of an approximate straight line portion. So if we have a slider prismatic pair here with link 5 and link 4, and that prismatic pair is, there is a revolute pair between link 5 and link 4, and link 6 there is a prismatic pair in which this link 5 moves. So long this coupler point moves along the straight line path, the output link, that is link number 6, does not move, and that is why we call it a dual mechanism. The input link 2 rotates continuously, but during this movement of link 2, as we see, there is hardly any movement of link 6. Link 6 does not almost move. So link 6 undergoes a dual, that is a rest period. So such a dual mechanism is very useful for various applications. Now link 2, during this movement, as we see, the link 6 moves, but during this period movement of link 2, this amount of movement of link 2, link 6 hardly moves. And that is possible only because this coupler point is going almost along a straight line portion from here to there. So this is the problem of a path generation, how to design this 4R linkage such that this particular coupler point generates this prescribed path. So this is a problem of path generation. As a further example of a path generation problem, let us look at this 6-link mechanism. Here again we have a 4R linkage consisting of these two red links and this yellow link, which is the coupler. And this particular coupler point of this 4R linkage generates this coupler curve. This coupler curve consists of almost two circular arcs. These circular arcs are of course approximately circular. Now during this movement of the coupler point along the circular arc, the center of the circle does not move. So I can join another link here which I treat as my output link. As a result, we get a dual mechanism such that the input link 2, which rotates continuously, but as we see, the output link, that is link 6, undergoes two dual periods. It moves, but for some rotation of link 2, there is no movement of link 6. For example, from here to there, link 2 is rotating, but as we observe, the link 6 is not rotating, because this coupler point is going along a circular arc and this point is the center of that circular arc. So there is no movement of this point, consequently output link 6 does not move at all. So it undergoes a dual mechanism. It undergoes a dual period and we get a dual mechanism that the input link 2 rotates continuously, but the output link 6 undergoes dual period. So the path generation problem is to design this 4R linkage such that this particular coupler point generates this prescribed path, which consists of two approximate circular arcs. As a simpler example of a path generation problem, let us look at the model of this film drive mechanism. As we see, here we have a 4R linkage with this red link as the coupler, and this particular coupler point generates the coupler curve, that is, it is the prescribed path through which this coupler point has to move. So if we now move this 4R linkage, as we see, that particular coupler curve is generated by the coupler point. Now this end of this coupler can be used as a hook which gets into the sprockets of the film and drives the film downward. Here it comes out of the sprocket, goes out and again gets into another groove, another sprocket, and draws the film downward. So this way it can be used for driving a movie film in a movie projector. If it goes very fast, the film also moves very fast. The critical thing is that it must move almost vertically here to drag the film downward, and then gets out of the film and again gets into the film and drags it downward. So this is another example of a path generation problem. We have to come up with these link lengths such that this particular path is generated by this coupler point. The continuous input rotation of this red link produces intermittent rotation of this blue link. Now this Geneva wheel, the start and stop of the intermittent motion of this blue link is very jerky, because it does not get into the slot smoothly and doesn't come out of the slot smoothly. So the start and stop of this intermittent motion of this link is jerky. To get rid of that jerky motion at the start and stop of the Geneva wheel, what we can do? We can drive this Geneva wheel by this coupler point of this 4R linkage. As we see, this is link 2, link 3 and link 4, and this is the coupler point. So if the input is given to the crank of this crank rocker linkage, then this particular coupler point gets into this slot and goes out of the next slot. And if we have a coupler curve such that the tangent to the coupler curve are along these two directions, then the entry and exit from this slot is very smooth. Consequently, we can use this particular coupler point to drive the Geneva wheel. So this is again an example of a path generation problem, because we have to generate this particular path by this point such that the tangent to the path are along these two slots at 90 degree. As a last example of path generation problem, let us look at this model of an 8-link transporter mechanism. Here we have a 4-link mechanism. Link 2, that is the crank, which is the driver, this is the coupler, and this is link number 4. And in this coupler, this particular point, we want to generate a curve which has a vertical portion, has a horizontal portion, and comes down. Now you see, if we drive this transporter mechanism, as we see that suppose this is an object which has to be moved through a number of stations, and at every station it must dwell. It must not move after reaching the station for some time, so that some operation can be done on this object. So if we drive this mechanism, because of this particular shape of the coupler curve which has been duplicated here, the transporter, let us note the transporter movement. It has been left, the object, it is now being picked up and pushed. Again it is left because this coupler point is coming down. Now this coupler point, due to this vertical path, is going up and again picking up the object, and now because of this horizontal path, it is pushed horizontally to the next station. Again it is picked up and pushed to the next station and left it. So it is this particular coupler curve which is causing this transporting movement from one station to the other for this object. So if I drive this as the input link which rotates continuously, let us look at the motion of this object. It is undergoing dwell in the next station, it is picked up, so the whole basis of the design of this transporter mechanism is based on this particular coupler curve here generated by this coupler point. This is the coupler of this 4R link. So this is another example of a path generation problem and its application to real life mechanism. Through a number of models, we have just seen the application of motion generation and path generation problems towards the design of some real life mechanisms. Of course, at this stage, our only objective is to learn the method to solve the problems of motion generation and path generation. The models of course provided the motivation that once we know this method, we should be in a position to apply these methods towards the design of real life mechanisms. To continue our discussion with various types of problems in dimensional synthesis of linkages, let me continue with the third class of problem, which we call function generation. In a function generation problem, the objective is to maintain a prescribed relationship between the output and input movement. That means to determine the kinematic dimension such that the output movement and the input movement are correlated according to a prescribed manner. The last class of problem we call dead center problems. In this type of problem, we have to design the linkage such that we can generate prescribed dead center configurations. So, we have four classes of problems in dimensional synthesis of linkages, namely motion generation, path generation, function generation and dead center problems. At this stage, we must emphasize that in the synthesis problem, we can talk of exact synthesis and approximate synthesis. That means the desired or prescribed motion characteristics are satisfied exactly over the entire range of movement, or it is satisfied only approximately during the entire range of movement. More often than not, it is not possible to use a simple linkage and satisfy the prescribed motion characteristics exactly over the entire range of movement. So, we should have to be satisfied when I use a simple linkage with the approximate synthesis. That means during the entire range of movement, the prescribed motion characteristics will be satisfied only approximately. There are various approaches to this approximate synthesis, and we will take up only what we call a precision point approach. While generating a motion, path or function over a given range, as I said, it is normally not possible to exactly satisfy the requirement at all configurations. So, in approximate synthesis, what we do, the desired characteristics are satisfied only at a finite number of configurations in that entire range. And these particular configurations, when the motion characteristics are satisfied exactly, are called precision points. Our next task is to choose these precision points in a better fashion. So, for the choice of precision points, what we do normally, initially we take Chebyshev spacing. What we mean by Chebyshev spacing? Suppose the motion characteristics has to be satisfied covering a range of a variable x starting from xi to xf. Xi is the initial value of x, xf is the final value of f. If the motion characteristics has to be satisfied in this entire range of x, then we choose say n number of accuracy points, n can be 2, 3, 4 and so on. There is a limitation on this value of n depending on the type of linkage that you use. Now, to choose the Chebyshev's accuracy points, what we do, we take the accuracy points say xj, which is equal to a minus h cosine 2j minus 1 into pi by 2n, where j goes from 1 to n. That means we take n accuracy points, namely x1, x2, x3 up to xn. And in this expression, the variable a denotes the midpoint of the range, that is xi plus xf by 2, and h denotes the half of the range, that is xf minus xi by 2. For the dimensional synthesis of linkage, just like kinematic analysis, two methods are available, namely graphical and analytical. We will start our discussion with the graphical method. Graphical method, we can start with three position synthesis. Let me now illustrate what we mean by this three position synthesis with reference to various types of problems, namely motion generation with or without coordination with the input movement, path generation problem with or without coordination with the input movement, and the function generation problem. we shall illustrate this method assuming that the linkage we are going to design is a 4R linkage. Before I explain the different types of problems with reference to a 4R linkage, let me continue our discussion a little bit with the Chebyshev spacing of precision points. As I said, suppose we have to satisfy the requirement in a range of variables starting from xi, that is x initial, to xf. We have already seen how to choose the various precision points xj. We have given the expression as a minus h times cosine of 2j minus 1 into pi by 2n, where n number of accuracy points are to be chosen in this interval from xi to xf, where j goes from 1 to 3 up to n. So, if I put x1, I will put j equal to 1 there, and n is already known to us depending on whether we are going for 3 accuracy points or 4 accuracy points. Accordingly, n will be 3 or 4. This expression can also be used to draw graphically. Whatever we get from xj from this expression can also be obtained from this simple drawing. What we do? We draw a semicircle, as we have seen, with xi xf as the diameter. This is a semicircle drawn with xi xf as the diameter. So, the midpoint of this interval, that is xi plus xf by 2, is our A. Similarly, this h is the half of the range, that is xf minus xi divided by 2. So, to obtain say 3 accuracy points in this interval, which are given as the Chebyshev's accuracy points, so that the motion characteristics is will be exactly satisfied at these 3 points, namely x1, x2 and x3, and everywhere else there will be some errors. What we have done, because n equal to 3, we have drawn a polygon, regular polygon of 2n number of sides, that is a hexagon, such that 2 of its sides are normal to this x-axis. 2 of the sides of this regular hexagon is normal to x-axis. Then the projection of these 3 vertices will automatically determine the Chebyshev's accuracy points given by this formula. This is x1, this is x2, this is x3. For example, if we have n equal to 4, suppose we are looking for 4 Chebyshev's accuracy points, n equal to 4. Then as before, we draw a semicircle here. This is a semicircle with xi xf as the diameter. Then we draw a regular polygon of 2n sides, that is an octagon with 2 of its sides perpendicular to the x-axis. One side, this is perpendicular to the x-axis, another side perpendicular to the x-axis. We inscribe an octagon with 2 sides perpendicular to the x-axis. Then the projection of these vertices of this octagon automatically determines the Chebyshev's accuracy points, namely x1, x2, x3, x4 in this range from xi to xf. xf is the final value of x, xi is the initial value of x. So, this is nothing but graphical representation of the equation through which we determine the Chebyshev's accuracy points in a given interval. At this stage, let me say what we mean by a guidance problem. Suppose we are talking of a 4-bar linkage namely O2, A, B, O4, where AB is the coupler. By motion generation problem with 3 accuracy points, what we mean that this coupler rod AB has to take up these 3 positions, namely A1, B1, A2, B2 and say A3, B3. That is, n is equal to 3. So, our objective is to determine this 4R linkage such that the coupler AB occupies these 3 positions during the movement of this mechanism. This is guidance problems without any coordination with the input movement. Suppose we have a guidance problems which is coordinated with the input movement, then the same coupler AB, when it takes up the first prescribed position A1, B1, I want the input link which is hinged at O2 takes up the position given by this line. That is theta 2, the angle made from some reference line here, this is theta 2, that is the rotation of the input link O2A. So, this is the guidance problem coordinated with the input movement. That means, when the coupler occupies the position A1, B1, the link O2A must come along this line denoted by theta 21. Similarly, when the coupler goes to the second position, namely A2, B2, the input link must be along this line as denoted by this theta 22. Similarly, when the coupler is the nth position, say AN, BN, which for n equal to 3 will be A3, B3, the input link must be along this line as given by theta 2n. So, this is what we mean by guidance problem, but coordinated with the input movement. Suppose again we consider the same 4R linkage with ABC as my coupler and C is the coupler point. So, by path generation problem we mean that we have to design the linkage O2, A, B, O4, the 4R linkage. We have to come up with the dimensions of that such that when the linkage moves, the coupler point C passes through these 4 prescribed positions, namely C1, C2, C3 and say C4. This is Cn, n can be 3, 4 or 5 depending on the problem statement. So, this is path generation without any coordination with the input movement. We are not bothered about the input movement as the coupler point goes from C1 to C2 or from C2 to C3. So, this is path generation without any coordination with the input movement. This figure explains what we understand, what do we mean by path generation coordinated with the input movement. Say O2 is the fixed hinge and O2A is the input link. So, what we mean that when the coupler point C is at C1, I want the input link O2A must be along this line O2A1, that is theta 21. This theta 2 is measured from some reference line. When the coupler point C goes to C2, I want the input link must be along this line, that is O2A2, and when the coupler point comes to Cn, the input link O2A must be along this line O2AN. So, this is what we mean by path generation coordinated with the input movement. Not only the coupler point has to pass through C1, C2, Cn, some prescribed points. When they pass through these points, the input link must take up these configurations, namely O2A1, O2A2, O2AN respectively. So, this is what we mean by path generation coordinated with the input movement. This figure explains what we understand by a function generation problem. Again, we are talking of a 4R linkage, namely O2, A, B and O4. O2 and O4 are the two fixed hinges. O2A is the input link, O4B is the output link. What we want, that the movement of this output link, which is denoted by the change in the angle theta 4 measured from some reference line, this movement of the output link is to be coordinated according to a specific function with the input movement, which is given by the change in this angle theta 2. That means the change in the angle theta 2, delta theta 2, we assume proportional to the input variable, change in the input variable delta x. Delta theta 2 is proportional to delta x, and the change in the movement of the output link, that is change in the angle theta 4, delta theta 4 is proportional to the dependent variable y. Change in the dependent variable y, that is delta theta 4, is proportional to delta y. That means, suppose we are talking of 3 position synthesis, we want when the input link is along this line, the output link must be along this line. As the input link moves through this angle and occupies this position, the output link must rotate by a prescribed amount as shown here, and the output link should occupy this position. Similarly, when the input link is along this line, the output link must be along this line. So, this is what we mean by function generation. The output movement delta theta 4 is coordinated according to a given manner with the movement of the input link, that is delta theta 2. We have just now explained what we understand by motion generation and path generation problem with reference to a 4R linkage, that is the movement of the coupler or the movement of a coupler point. 3 position synthesis means that the exact motion, specified motion characteristics, required motion characteristics will be satisfied only at 3 isolated configurations. We have also seen that these 3 positions where the motion requirement will be satisfied are chosen according to the Chebyshev spacing in a given range, which ensures the error between these accuracy points will not be too much. So, the motion generation we have explained with respect to a 4R coupler link. So, we have explained the path generation. We can start with 2 position synthesis without and with specified input movement. This we will take up in the next lecture. So, let me now summarize what we have learned today. We have defined the problem of dimensional synthesis of a linkage, and then classified the various types of problems which are encountered in dimensional synthesis, namely motion generation, path generation, function generation and dead center problems. In our subsequent lectures, we will develop both graphical and analytical methods to analyze these problems. We have already seen that once we are capable of solving these problems, then these methods can be very useful towards the design of real life mechanisms. and this vector is omega 2 squared into P2O2. Now, this vector is completely known, so let me try to draw this vector at P2. Vp42 was 10, omega 2 is 2, so 2 into 2, 4 into 10, 40 centimeter per second squared, and it is in the horizontal direction, but double of this length. This is 40 centimeter per second squared, and this vector represents twice omega 2 cross Vp42, and AP42 I know is vertical, so I draw a vertical line through this point. This was horizontal, so it is a 90 degree, and these four vectors, these two vectors represent this vector represents this, and this vector is in the vertical direction, and all these three vectors summed over must give me AP4, which is horizontal. So I draw a line horizontal, and wherever they intersects, that gives me the point P4. According to this vector equation, this O2 P4 represents acceleration of P4, and this represents acceleration of P4 as seen by an observer on body 2. So this diagram represents this vector equation, and it is easy to see because this is 40 horizontal line, this is 20 which is also horizontal line, so this must be 20. So AP4 I get as an answer is 20 centimeter per second squared in the horizontal direction from left to right. So this example clearly shows the power of considering the instantaneously coincident points on various links when we have sliding joints on rotating links. Now that we have completed velocity and acceleration analysis by graphical method, let me show you how to carry out this such velocity and acceleration analysis through analytical method. In analytical method, just as in the displacement analysis, we start with the loop closure equation. That means we represent the link lengths and sliding displacement as vector quantities and go through each loop that is present in the mechanism and write the corresponding loop closure equation in terms of these vectors. The first step for carrying out the velocity and acceleration analysis is obviously to complete the displacement analysis. Now that this loop closure equation is valid for all instants of time, we can differentiate both sides of such loop closure equations to complete the velocity and acceleration analysis. Successive differentiation of this loop closure equation with respect to time will give us the required velocity and acceleration relationships. I would like to mention one point here, that in the displacement analysis through analytical method, we always get nonlinear algebraic equation. Whereas, if the displacement analysis is complete, which is always necessary to carry out the velocity and acceleration analysis, for velocity and acceleration analysis, we always get linear equations in the unknowns. That means the problem is much simpler. As an example, let me start with a 4R linkage. That means 4 links connected by 4 revolute joints. संजय जब बोलना तब शुरू करेंगे. Let us look at the diagram of these 4R linkages, namely O2, A, B, O4. As in the displacement analysis, we set up a coordinate system, Cartesian coordinate system xy with the origin at the revolute pair O2. The fixed link is represented by O4O2, the input link by O2A, the coupler by AB, and the follower or the output link by O4B. For this given configuration, that is, if theta 2 is given, by displacement analysis we can obtain theta 3 and theta 4. After doing this displacement analysis, that is, knowing theta 3 and theta 4, we should be in a position to carry out the velocity analysis. What do you mean by velocity analysis? Let us say the input velocity, that is theta 2 dot, the angular velocity of link 2 is prescribed, and we have to find out the angular velocities of link 3 and link 4, which are given by theta 3 dot and theta 4 dot respectively. Obviously, everything is measured positive in the counterclockwise direction. So, let me write now the loop closure equation. Vector L1 plus vector L2 plus vector L3 is vector L4. This is exactly the same as we did in the displacement analysis. So, let me write now these two-dimensional vectors in terms of complex exponential notation, that is L1 plus L2 e to the power I theta 2. The vector L2 can be represented by this complex exponential notation. Magnitude is L2 and the orientation of this vector with the positive x-axis is given by theta 2. Similarly, L3 vector is L3 e to the power I theta 3 is equal to L4 e to the power I theta 4. As we know, e to the power I theta can always be written as cos theta plus I sin theta. So, what we say, we equate the real and imaginary parts of this particular complex equation, which is same as saying equating the x component and y component of two sides of this vector equation. That way we get L1 plus L2 cosine theta 2 plus L3 cosine theta 3 is L4 cosine theta 4. Equating the imaginary parts, we get L2 sin theta 2 plus L3 sin theta 3 is L4 sin theta 4. So, this complex equation is equivalent to two real equations, which I mark as equation number 1 and 2. Now, these equations are valid for all instants of time where theta 2, theta 3 and theta 4 are functions of time, whereas the link lengths L1, L2, L3, L4 are constants, time independent constants. Because these equations are valid for all instants of time, I can differentiate both sides of these two equations with respect to time, and I can write from the first equation